Hi, myself Indradeep Kumar, Assistant Professor, Institute of Aeronautical Engineering. In last video, we had seen some basic concept about the structure. Okay, that means the evolution, or you can say the history of the aircraft, the structure, how those things are there. Now we will start the module according to the syllabus. So in that, first we will see the basic concept of aircraft structure. That means how the load will act, or whatever the things are, or components are there. That we will see in this video. So first lecture topic. So these things we will cover in this video. So first one is basic equation of linear elasticity. So here we will see how the linear elasticity is there in the last class also. In last video I discussed about the linear elasticity. So we will see that equation. Then we will go for the concept of stress. The stress also explained who invented and how these things are acting. So how their formulas are there, how the equation we can form. So these things we will see in this one. And after that, we will see analysis of stress at a point. So when stress is acting, or that means when force is acting at that particular point, what about the stress will be there, how it's behaving. So these things we will see in this video. So first, let's start with the basic equation of linear elasticity. So what happens when we will discuss about the structure things, like now if suppose this structure is there, right, randomly. So now that force can be applied by this also, like this. Force can be applied inclinedly also. Some force may act over the surface also tangentially. So how these things are there, based on that only we can say how much stress is acting. So first, so but we will see the evolution of deformation and stresses arising with a solid object under the action of applied load. Meaning what? How the deformation will occur when the stress, that is force per unit area, is acting on any surface or any solid body. So that we will see. So what is that? If time is not explicitly considered as an independent variable, meaning what? That is, it's not depending on the time. Right, we are not considering over the time, like suppose if we will keep 5 kg weight here and after 1 year or 2 years, like that we will see no. And so we are not considering time, only just force and area. So these things we are seeing here. Okay, so if we are not considering the time, then this analysis is called as a static analysis, or analysis of the static force. Now, if we will consider the time also, like with the time, if any changes are there, right? So that becomes the dynamic of that one, right? So means if we are considering the time, then it becomes a structural dynamic analysis. If we are not considering the time, then it's a static analysis. So now, what assumptions we are making for that? These two are the first. A small deformation is there, means after applying the stress, only very small deformation will be there. Second, they behave like elastic material. Whatever the property of elastic material is there, so they behave like a elastic material. Now, if we'll see in that the 3D, then what happened? So 3D formulation, what? A set of 15 linear first order PDE is involving. A set of 15. What are those? So just see. For the displacement, 3 component, means with that we will get the 3 component, like in x, y, z coordinate. Then similarly for a stress field, 6 component, 3 including this one, and a strain field having again 6 components. So total 6 plus 6, 12 plus 3. So total 15 component acting over there. Now if we'll see over the 2D, then what happened? Only 2. That means plane stress and plane strain. Why? Because in that also we can see in 2D only the xy coordinate is there. There is no z coordinate. It means only one plane only we can consider. So they are only, that's why we are saying this as plane. 2 axis is there, so it's a plane. So plane stress or plane strain problem. Next is, most situations not possible to develop analytical solution. Sometimes is there that with this we cannot find the analytical solution. Okay, then what happened? And which type of materials are there? Those are bars, beams, plate, cells. In these we cannot directly find the possible developed solution or possible analysis. That means if suppose a strain is there, so how much possibilities of a strain is there, that we cannot find directly in this case. Okay. Now come to the concept of stress. So how a stress will be generated, how a stress is behaving or acting on the body. So a state of stress in a solid body, meaning what? It's a measure of intensity of force acting within the solid over the area whatever we are considering. Right. So it's obvious when force is acting on somewhere, so how the force is distributing, right? So just see here in this figure, we can see this is the body and over this cross-sectional area of this one. So just see force is acting here, force above that one, the normal is acting here to the surface. Normal always act to the surface. So this is normal and here the moment is acting. That is moment, you can see how that is named as couple also. So just see force is acting in this direction, right? Normal acting perpendicular to the surface and moment is. So this is the free body diagram when a force is acting on any surfaces. Okay. Next, so just see from here. So this is the actual body what we have. That's the solid body. Now let's cut the part. After cutting, what we will get? We will get these two parts, right? So now we are considering here. So just see here, this because this is the part of this one. So when force is acting, so force is in this also it will act, and moment will also act, right? So now from this we are drawing the free body diagram of the body. So now with free body diagram, what happened here? This we will get the area vector also. This n is the area vector, that is which is the perpendicular to the surface of this one, right? So now if a small surface on the cut, that means now just see in this only, this part, okay? What are the things acting? So force along the normal direction, this normal vector, that is the area vector, and moment along the normal vector. So that's why here just see in this, you can see the small n is there. Okay, so that shows along the normal direction. Now from this, if you will just join here the force and moment, this is the resultant force of the resultant force acting on the body, right? So this is, you can say, how once force is applied, body will get break into two pieces. Then how the force, moment or couple and the area vector acting on the surfaces of the broken body. Now just see, let's a small surface area AN already have that N along the normal located at a point P on the surface generated by the cut, means what? Here. So this part, a small, this area AN, we are taking this small part where we are considering. So this is our area AN, or you can say the elemental area, right? Having the equivalent force Fn, means in all the directions that force is acting, that is Fn, and couple Mn, right? So now what happened? Limiting process of area, that is what? Concept of stress vector. So that stress vector, that is denoted by tau. So this we can say this is the tau, and again same everything we are taking in terms of n, that is normal to that one. So tau n will be equals to what? Limiting here d area. Now the thing, it depends on what? How much area we can take. We had taken this small area an, right? It's not necessary, you can take the whole area also, right? Or you can take the zero area also. So that's why that area approaches to zero. So just see DAN approaches to zero, that is limiting to zero, right? Or limiting process of area. That's why your name is limiting process of area, which will be equals to tau is what? Force per unit area. So here our area is what? dA, that is small elemental area, right? So tau n will be equals to limiting DAN tends to 0 Fn by DAN. Okay. Now the existence of this limit, right? So that's why just to explain fundamental assumptions of continuous mechanics. Continuum mechanics is what? It should be continuous. We can take any small element, okay, for that particular any reason, and over the entire span we can integrate it. We will get the total force. So now let's see, when couple is 0, what happened? There dA will be also, that is, or dA is 0, then couple will be 0. If there is no area, then no moment will be there. So if DAN is approaches to 0, then couple also will approach to 0. Now, so what is the couple? Couple is the product of a differential element of force by a differential element of moment arm. Moment arm is what? The distance. Couple is simply force into perpendicular distance. In another word, you can also remember couple is force into the perpendicular distance. That's why here it's given the moment arm, about that arm if it's acting. Or just take the example, suppose here this is the body and force is acting over here, right? This is the fixed part, so that this length is L, right? Then the moment because of this force F will be on couple will be force into L, right? That length. So that will be whatever the distance is where the fixed point where they generated the moment. Okay, that distance you have to multiply with the force. So this is the arm over that the force is acting. So that's why here it's named as the moment arm. Now total force will be acting in differential element what? In that dA, just integrate it. So Fn is dA tau, or you can say just take this one, right? What we have, tau n is equals to Fn by dAn, right? So take this side, cross multiply. So this Fn will be equals to dAn into Fn. So this will be our what? The force acting on that element. Remember, this is the force acting on that element. Still we are taking the elemental part only. Once we will find for the total area, then only we will get the total force acting on that body or that part. Now what will be the unit of the this one? What? So unit force unit is what? Newton. Area unit is meter square. So the unit will be Newton per meter square or Pascal, which is same as the pressure. So that's why in my last video also I explained, when we are considering the solid body, then it's what we are saying, it's a stress, and for fluid we are saying it's a pressure, having the same formula, same unit. Okay, just the thing, it's either it's a solid or fluid. Now come to the next. So now again the same, small surface area En located at point P. Now at that particular point we are considering, because I already said that point load, yeah, okay, on the surface generated by the cut. What? So this is our the surface. Okay, in that surface, okay, we are taking a point P anywhere over that one. Now in that we have to find how much of force will be there or the couple will be there. Similarly again equivalent force Fn and couple will be Mn. Limiting force area, limiting process area will be what? Again delta A tends to 0. That will give the what? Concept of the stress vector. So now in this case just see, in previous case we had seen like this acting in this direction. So now how exactly the resultant of that will be there. So this is the dA, or just here, take this first here, dA2, we consider this one. Okay, so now here the stress is this one acting tau 1. Okay, in the second area this will be tau 2, this will be tau 3. Similarly to this figure, right? Force moment. Okay, so now dA, here sigma is stress. So sigma 1 stress acting on the first surface, sigma 1, sigma 2, sigma 3. Now once we will introduce this tau, that stress vector, then just we have to consider in the plane what is there. So this is the first plane. So and just here sigma 2 is acting in this direction. So opposite to that plane tau 2 1 will act. Now here sigma 1 is in this direction. So this is aligned with this one. So 1 and 2. So tau 1 2 will be acting in this direction. So sigma 1 and sigma 2 will be here. So sigma, because of that, tau 2 1. So simply it's a, you have to take care that in which direction it's acting, that is in which plane. Remember when we are considering that 1 2, that is acting in the plane 1 2, like just x y. So this is your y, this is your x. So we are seeing in xy plane. So similarly here 1, 2 means 1, 2 plane. Here 2, 1 is there, means it's a 2, 2, 1, it's acting from towards 2, that is 2, and acting it's towards 1. In this case, tau 1, 2 is there, so from 1 to 2, it's acting. Similarly, this one, tau 3 is there, so in this direction, tau 3, 2 will act. In this direction, tau 3, 1 will act. So because this is the sigma 3, this is 1, 2, 3. So here 3, 1, this is 3, 2. Here similarly the tau 2, 1 because of this sigma 2, and here tau 2, 3. Means in which direction? So this is in this plane, this plane. So all these three are in different plane. In which plane is there? According to that only you have to assign the value. So like suppose if this is I3 direction, this is I1 direction, this is I2 direction. So now just see here again, I'm repeating this one. How to this one? So first take this one. So this is in this plane, one I1 and I2 plane. So whatever here we will take that I1 and I2. So now come to again this one. So in this direction it's acting, right? So this is I2 direction, from where? In which side? Opposite to that one. So that's why here tau 1 will be there, but 1, 2, 2 it's acting. 1 is here, 2 is here. In this direction it's acting. So see here, tau 1, 2, 2. Now just opposite to that one, it's acting oppositely, right here. So now just see, this is 1, sorry, this is 2, this is 1. But this is vertically acting. So now this one will be what? 1 and 3, because this vertically will be there. So tau 1 and 3 will act here. Now come to the plane, this one, that is I3 and I2. Right, but this one is I1. So here in this direction it's acting, right? So 2, 1. In this direction, this is our 2 and this is our 3. So upward is 2, 3. Okay. Similarly here, this is 1, like I1. So 3, 1, 3, 2 and sigma 3. Now clear? Now how that dot will be there? So component of each stress vector, that is sigma, acting on 3 forces. So what will be that? Tau 1, first that one, this sigma 1 in I direction, in I1 direction. Similarly sigma, that is after that, tau 1, 2, I2, tau 1, 3, I3. So now just see the total component from here again in this figure. So tau 1 is acting in this direction, tau 1, 2, sigma 1. So sigma 1 in this and remaining these two. So similarly here, for first, sigma 1 is acting in I direction, so sigma 1 I. Then tau 1, 2 acting in which direction? So just see, tau 1, 2 acting in 2 directions. So tau 1, 2, that is tau 1, 2 in I2. Tau 1, 3 acting in I3 direction. So tau 1, 3 in I3. Okay. So this sigma 1 is what? Direct stress or normal stress. These two are what? Shear stress along that surface. Just to explain that these two should be acting. That means if this tau is acting in this one. So here sigma is normal stress, tau is what? Tangential stress or shearing stress. So now both act on the force normal to axis I1 in the direction of I2 and I3. So these two will act towards I1 and in the direction of I2 and I3. Okay. So now again same. What will be this one? Area, that force per unit area. Right. Now just here, this dual code shows engineering stress component. Which one is that? This positive. So positive force means what? It should be outward normal to the face. Means now you can say in another word that sign convention. Means if inward force is there, then what we have to take. If outward force is there, then what we have to take. So if inward force is there, then we can say it's a negative force. Means if acting inwards. If acting inwards, negative force. If acting outward to the plane, then we can say this as the positive force. So the outward normal to the face, that is normal pointing away from the body. So wherever this will act, this is just here like sigma 2, right? This is normal to the this surface. So this is going away from the surface. Means this we will take as positive. If this will go inside of the body, right, then the same force we can say this is negative of that one. So this will show the sign convention how we will take that one. Whatever the force is there, if it will act away from the surface, or you can say perpendicular to the surface and it's moving away from that one, then we can take this as positive. If it's coming towards the surface, then we can take as negative. So totally how many components are there? Just see here. Sigma 1, tau 3 2, tau 2 1. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So in this figure, you can see all the 9 components of the stresses acting. In that, 3 are direct. That is sigma 1, sigma 2, that is here sigma 2, sigma 3. So these 3 are the direct stress or normal stress, and remaining 6 stresses, these are acting on the surface. So here this is acting over the surface, that is CR1, this also acting over the surface, okay, or you can say the tangentially to the surface. So these are the shearing stress or shear stress. Now next, what is force? Force is vector quantity, right? So in that case, what happens? 3 component of force vector, that will give you the first order tensor. If 9, in case of stress, 9 quantity is there, then that will be of the second order tensor. Right, now what is tensor? Right, if they have the direction, then what you can say? Vector, there is no direction, only magnitude. It's a scalar, and the third, there is no magnitude, no direction. Okay, that's so. Now bending stiffness of the beam and mass movement of inertia. So these comes under the second order tensor. Now for any volume, how? Like that means any body is there in equilibrium, then how is there? So volume equilibrium equation, how that body or anything is there in that volumetrically, it's in equilibrium. Okay, so first, what is that? The stress varies through a solid body. So in this figure, you can see, just see a 3-dimensional body is there, that is 3D body having some volume, right? So again here, what happened? 9 component will act. In that 3 will be that norm direct, and 6 will be indirect one. So just see here now in all the directions. So sigma 2 is acting here, sigma 1 is acting here, okay, then sigma 3. So now once from this part to this part, if you will go inside the volume, then what happened? Definitely some change will be there. By what amount the change will be there, right? So that will be sigma, that is delta sigma x by delta x. Now in this, whatever the direction is there, in that direction, if suppose sigma x in first direction, right, then here this will be x1, okay. If here x2, then here also x2 will be there, right? So this will be the change in moment, that is the additional stress will be there. So now let's see, axial stress component at the negative phase, that is sigma 2 are negative. Why? Because sigma 2 is here. If sigma 2, that is at x2, is an analytic function using a Taylor series. Now with the Taylor series, expansion is there. I hope you know the Taylor series. If not, then just see this one, what will be there. So sigma 2 of x2 plus dx2, meaning what? x2 in the original direction and dx2 change in that direction will be what? Sigma 2 x2, that is this one, plus the total change in that particular direction. So here you can say in the summarized form, delta sigma 2 by delta x2 of this whole thing, dx2 to all the term, whatever the stresses acting in that particular direction. Now if suppose body force inside the body is there, they will have the mass, so definitely they will act as a gravitational force or any. So if suppose body force is B, what is that? Gravity, inertial, electrical and magnetic. If these things are there, so just their component will be what? That body force B will be in which direction it's acting. So B1 will be in I1 direction, B2 will be in I2 direction, B3 will be in I3 direction, right? What will be unit? force by volume. Now here we are considering for the volume, not by the area. So force by volume. So that body force will be is force by volume. Then unit will be what? Newton per meter cube. Okay. So now let's see again this one. Whatever the direction is there, here tau 2 3 is there. So d tau 2 3 by dx1 and dx1. Similarly for sigma 2, d sigma 2 by dx2, dx2. So whatever the direction is there, there's a small incremental changes there because of this what volume. If at this surface sigma is acting or tau 2 1 is acting, then over this that will be increased by tau, that is tau d tau 2 3 2, that is d tau 2 by dx into dx, the small increment in that one that will get added to the opposite of that particular surface. Force equilibrium is what? When that body is in equilibrium. So it's obvious whatever the force is acting in all the direction, their sum must be equal to 0. Then only we can say the force is the body is in equilibrium. So for that, if force is not equilibrium or that body is not equilibrium, suppose some force is acting more in that direction, the body will start moving. If body is not moving or there is no deformation, then we can say no, that force whatever is applied over that body is in equilibrium. So means the overall sum of the total forces whatever is acting right on the body must be equals to 0. Means what? Direct stress, tangential stress and body force. Okay, the sum of all should be equals to 0. Then only we can say it's in equilibrium, and this must be satisfied at every point. It's not like that, okay, over this body here it's 0 and here it's not. If here it's not 0, then here some deformation or change in this will be there. So everywhere all the forces must be there, sum of all the forces must be equals to 0. Then only we can say it's equilibrium. If it's not 0, then the deformation will be there, right? So that is equilibrium should be enforced on the deformed configuration. Means wherever the deform is there, that you have to just consider this one. If this is there, means that body is in equilibrium. If this is not there, then definitely some deformation is there. Now, linear theory of elasticity. So what is that? The first, see the assumptions. What is the assumptions? Assumptions that displacement of the body under the applied load are very small. So what we are considering here assumptions, it's not like that body is this one and displacement will be this much. No, that is not possible. Then we cannot use this elasticity, because in last video also we have seen up to the elastic limit only it can again regain to the original position. No breakage will be there. After once it reaches to elastic region and move to the plastic region, then some deformation will be there. So that's why we are just considering the very small displacement will be there as an assumptions, and hence difference between deformed and undeformed is very small. If small deformation is there, so definitely the difference will be also very small. Now next is force equilibrium we are seeing. Now next is moment equilibrium. Same thing, sum of all the moments acting on that body must be equal to 0. So just see here in this direction I1, okay, tau 2 3 minus tau 2 t, tau 3 2. So just see here 2 3 means what? If suppose this is 2, this is 3, right? 2 to 3, then 3 to 2 will be just opposite to that one. So if this is acting, this we can say 2 3, then this will be 3 2. So these two are opposite. Opposite means what? Their sum will be definitely equal to 0. And this is only the principle of reciprocity of shear stress. Reciprocity, that means in all the directions there must, that moment must be equal to 0 for a balanced or equilibrium body. So in this case what happened? Only 6 independent component in 9 stress component, right? So here why? Because of the equilibrium, 3 are constant, so body is not moving, so only 6 are independent out of 9. Or you can say another symmetry of the stress tensor. Now surface. First what we had seen, first one force equilibrium, then moment equilibrium, next is the surface equilibrium equation. And the outer surface, what happened? So let's see, stress acting inside the body, right, and externally applied surface or surface traction, that externally applied force. These two must be equal. If these two are not equal, that body won't be in equilibrium. If internal force, internal energy or whatever is there internally, it's acting, that must be equal to the external force. If any one will be more, okay, then if suppose external force will be more, then we can say that body will get compressed depending upon both the direction, or if one side is fixed. So these two must be equal, then only we can say their surface is in equilibrium. If it's not, then maybe like surface is this one, and after deforming, now this will be here and this will get like this. So some small deformation will be there. So internal as well as external, that is inside the body whatever the stress is acting, and outside applied must be same. How? So let's see that the tensor again same, Ti in I1 direction, T2 I2, T3 I3. So total will be equals to this in the vectorial form. So here in this figure you can see the free body of what? Differential tetrahedron, bounded by how many? 3 negative faces, okay, to I1, I2, I3, the fourth face ABC of area DN. So now just see again with this 3 negative forces cut, whatever is there. So external force acting on this one. Now come to here, I1, I2, I1, I2, I3, and the third face of back side of the tetrahedral having this what? This yellow one is DA2. This one surface, 2, 3, and the third inside of that DA2. That is, sorry, DAN. So this yellow part is what? DAN. How stress is acting? So see here in this part again, tau 21, tau 23. Here you can see similarly in all the direction these stresses will be acting. So now in case of I1, I2 will be there. So tau 1, I1, tau I2. Similarly in these two, I2, I3, so tau I1, tau I2, tau I3. In this case 1, 3. Similarly in the previous figure already we drew the FBD, that is free body diagram. In that whatever the plane you are taking, with that component just you have to add. If these two are taking, then if 2, 3 is there, so here 2, 3 or 3, 2 will be there. In this case 1, 3 is there, so 1, 3 or 3, 1 will be there. Now force equilibrium, that already we had seen, the tensor will be what? Sigma 1 and 1, tau 2 1 and 2, tau 3 1. So in N1 direction sigma 1 force is acting, that is stress. In tau 2 CL stress is acting in N2 direction, and in N3 direction tau 3 1 is acting. So this is the total when the force is in equilibrium. Now what about the body force? Right, body force here it will be 0. Okay, so body force term vanishes since it has a higher order differential equation. So when we will consider in that body that having higher order differential equation, that is even if higher, even if suppose just for an example like 0.2 is there, if you will multiply with 0.2 you can say 0.04 will be there. So once you multiply the smaller amount, even it becomes more smaller. So similarly higher order differential is there, that becomes even more smaller, and hence we can remove it, or we can say it's a vanished. Okay, now let's see. A body is Situ in equilibrium if equation 1.4, that already we have seen, is satisfied at all the point inside the body. And equation 1.9 is satisfied at all the point in external surfaces. Right? So let's see here. Right? So this all must be equal to, the sum of all the forces must be equal to 0, then only this will satisfy, our force will be in equilibrium. Now next, analysis of the state of stress at a point, a state of stress at that particular point. Already told, now we will focus on one particular point. What is that? So it is defined as what? Once the stress component acting on three mutually orthogonal faces at a point R node. That is what, when that force is acting three mutually perpendicular surface. Okay, so how that will be there? So the stress component acting on an arbitrary face, any particular face. It's not necessary, but that should be fixed. It's not like that we are considering the left face and then we will go for the right face. So who found that one? That is by the Cauchy. So that's why their name is Cauchy tetrahedron. What is that? With a fourth face normal to unit vector n. Okay, arbitrary or n of arbitrary orientation. So now any particular force will be there, just start rotating to that one, right? Or rotation about that particular face. So see, these three are there. Now this fourth one we are taking in that one. So there in this direction, if it's there here, so the resultant of these two by the parallelogram law, we can say this is the resultant of what? These two forces. In which direction? In the direction of that plane. So this is what? Stress on the face normal to n. This is stress on three normal faces. So in this direction, this direction, this direction. So this is stresses on three normal faces, and this is what? Stress on the face normal to n. So just see the difference. This is three normal faces, whatever the normal faces are there over that one, but this is the face which is normal to the unit vector, not to this one, normal to the unit vector. So again this one, the now force will be equilibrium is what? All the side whatever the force is acting, that must be equal. So here what is acting? Tau 1 d1 one side, then around the second phase, that is area, tau 2 dA2, tau 3 dA3. These sum must be equal to what? Volumetric, that is body force, into dV plus tau dA, that is tau and dA. So if these two are equal, that is sum of all the shear stress, okay, and sum of body force plus traction force, then we can say the force is in equilibrium. Okay, now divide by dAn. So what we have? Tau 1 dA1 plus tau 2 dA2 plus tau 3 dA3. Left hand side. Right hand side, tau n dAn plus b dV. Okay, this is there. Now divide both sides by dAn. Let's divide. So here dA1 by dAn. Here also dA2 by dAn, dA3 by dAn. Okay, so dAn, dAn. Okay, now just see here. What happened? This will get cancelled. Okay. Now dA by A will give you what? Unit vector in the direction of n component. So this will be your tau 1 and this will give you unit vector, area unit vector n1. Okay. Plus similarly A2 by An. So this will be tau An. So this will give you what? Tau n2 and plus tau. Similarly this will give you n3. Which will be equals to what? This tau, and because these two get cancelled, right? And plus already we mentioned that body force is what? Negligible, that vanishes. So this term will be 0. So finally what we will get? Tau n will be equals to tau 1 n1 plus tau 2 n2 plus tau 3 n3. This already equation we had seen also. For equilibrium, this must satisfy. Okay. Now in 3 stress vector means what? Sigma, tau 1, tau 2 in that range. So then again the sum of all will be 0. So in n1 direction whatever the stress will act that one. In n2 direction all the stresses. In n3 direction all the stresses. Sum of all these will be equals to this one. So same here, just this tau 1, the total acting in 3 dimensions. Here we are taking the tau 1 d1, that is in one direction of 1. Okay, here once we will take the all the 3 dimensional, then these will come. So sum of all these must be equal to the tau n. Now the thing, how to determine the direct stress, that is sigma n. So just see, to determine the direct stress sigma n, project this vector equation in the direction of n. Whatever is there, just take the projection of that one. So what? We have tau n, okay? So just see here this one. Tau 1 I1, sorry, sigma 1 I1, sigma 1 2 I2, tau 1 3 I3. Now instead of I, everything will be in the projected to the n, that is along this plane. Okay, so now wherever I1, I2 is there, that all will change to what? N1, N2. So now sigma 1, N1, tau 1 2 N2, tau 1 3 N3. Okay, similarly tau 2 1 N1, sigma 2 N2, and then tau 2 3 N3. So let's see here, all just shifted to from what? I to N plane. Similarly tau 3 1 N1, tau 3 2 N2, okay, sigma 3 and 3. So all I projected to in N plane. Finally, what we will get? Just multiply with this one. So now this to all the elements. So sigma 1 and 1 square. Okay, then sigma tau 1 2 and 1 and 2. Okay, tau 1 3 and 1 3. So after multiplying this, that is just expanding the bracket. Okay, or let me expand. So let's first multiply with this n1 to all the term. So what happened? First we will get sigma 1, that is in this one, the equation. Sigma 1 n1 square. After this n1 multiplying to this one, so plus tau 1 2 n1 and 2. Then next will be plus tau 1 3 and 3 into n1. So now this got over. Now multiply here n2 to these two terms. So plus tau 2 1 n1 and n2. n1 already is there, n2 we are multiplying to all the term. Plus now this n2, so here, so sigma 2 n2 square. Then plus n2 multiplying here, so tau 2 3 and 3 into n2. This also multiplied. Now here. Now multiply n3 to all. So what we will get? Tau 3 1 n1 n3 plus tau 3 2 n2 n3 plus sigma 3 n3 square. Now collect a square term like this one, and this one. So what we will get? Sigma 1 n1 square plus sigma 2 n2 square plus sigma 3 and 3 square. So just see, after collecting all the term, now next what happened? This, so tau 1 2 n1 n2. Okay, and here with the direction. Okay, once you will multiply, this all becomes twice of that one. So just simplify this, you will get this equation. So overall sigma in the plane of pi, that will be what? Okay, this is, so pi is the total area that multiplied here. So that becomes sigma pi, and this will be the final stress, that is the direct stress acting on that plane or that particular point. Next, a stress component acting in the plane of face A, B, C. That is what? Tau over that surface A, right? So just see, again now, by project this one along the vector S. Okay, so here, just see, in this direction, we are now projecting. So similarly, just whatever the n1 will be there, like here, this will be there, this remains same, only n1 this will multiply, this will be s1, s2, s3. Similarly, s1, s2, s3. So now, sigma 1, n1, s1, sigma 2, n2, s2. So like this only. So here just you have to change I1 projected to n1. So I becomes n1. Now we are projecting to s. So now this n1 becomes s1, and again the same way you have to do, and you have to expand, and you will get this. Okay. So now there is equation, this one in n plane, and this is in s plane. Okay. Once the stress component acting on three mutually orthogonal faces are known, that is whatever the direction is in XYZ direction, the stress component on the face of arbitrary orientation can be readily computed. Meaning what? Once the forces is acting on these three mutually perpendicular or mutually orthogonal faces, then we can calculate all the stress component easily. Okay, so now depending upon what, how much information we require. So let's see how much information is required to fully determine the state of a stress at a point P of a solid, whatever the things are there. How? By this we can say. Okay, so now what is the principal stress that we will find? So if there is a phase orientation for which the stress vector is exactly normal to the phase. So just see a principal stress, meaning what, this word is very important. A stress vector is exactly normal to the face. Means a stress vector must be perpendicular to that face, should be there, then we can say that is the principal stress. Okay, so now just see what does a particular orientation that mass is exist. If it exists, then only we can find, okay, further let's analyze or find the principal stresses are there or not. So first thing you have to see this one. If this is there, then okay, you can go for the next. Okay, now if this is there, then we can find or we can analyze the principal stresses. Okay, so now over that face, what will be there? The tau n will be sigma P and N. So tau n that in that plane, because we found in this plane. So in this plane, whatever this one is there will be what? Sigma P into N in that plane. So now this sigma P is the principal stress. Okay. So now this is still what? Unknown is there. So we have to find this one. Right. So how we will find? Here is the formula. What? Sigma 1 minus sigma 2, tau 1 2, tau 1 3. Similarly, for in this, whatever is the acting, just now we are seeing here, these forces. Okay, so just see here in diagonally we can see sigma 1 minus sigma 2, sigma 2, sigma 3, sigma 2, sigma 3 to sigma 1, and in this case tau 1 3, tau 1 2, tau 1 3. So here in this row, tau 2 1, okay, tau 2 3. So just see how you will remember this one. That is the easier. In first row, first column, you are just moving this one. So 1, 2, 1. This is at the position of 1 and 2. Okay, in this way. So 1, 2, third position, 1, 3. Now in second, so 2, 1. This should be 2, 2, but here sigma is there, and this is 2, 3. So now third, so T 3 1, tau 3 1, tau 3 2, and then sigma 3 minus sigma 2. And this unit vector in the direction of this one. That unit vector 1 and 1 and 2 and 3. That is in that particular plane when we are projected. This equate to 0, you will get what? The principal stress value. So now after solving this determinant, okay, equate to 0, you will get the principal stress value. So now determinant of the system must be equals to 0. Then what happened? We'll get non-trivial solution. Yeah, right? So now once determinant, we are equating to determinant to 0, right? This determinant to 0. So if determinant is 0 means they must have non-trivial solution. And with that only we will get what? The stress invariant, that is sigma 3 square minus I1, that is identity matrix, sigma square I2, I3, okay, and that is called as stress invariant. So in that particular, this will be there. So now what we are getting this one is only the principal stress. Okay, how many trivial solution is 3? So just 3 solution, sigma 1 2, sigma 2 3, sigma. So these are non-trivial solution for the direct cosines. Now, so why here the cosines is there? In that particular angle that will be there. Now in case of homogeneous equation, what happened? Arbitrary constant should be there. That arbitrary constant, what happened? Enforcing the normality condition with that whatever. So now where I is what? N1 square, N2 square, and N3 square. This already we had seen in this equation here. N2 square, N3 square, N1 square. So instead of that, here we used I1, I2, I3 in this equation. Okay, so you can see this and the earlier equation also are same only. Now, rotation of stresses. Okay, so if that will be rotated, then what happens? Then definitely their component will change. So it should be like I1, I2, I3. Similarly for sigma 1, sigma 2, sigma 3, that is sigma 1 star, sigma 2 star, sigma 3 star, tau 2 3 star, tau 1 3 star, tau 1 2 star. So this is the star represent what if after rotation what will be there. So orientation of basis J star relative to J. So J in that how the rotation will be this one. So now the matrix will get changed also, right? What is that? Matrix of direction cosine or rotation matrix, that will be what? Cos of I1, I2, similarly cos I1, I2, cos I1, I3, cos I2, I1, I2, I2. So wherever the position is, just see again to remember it's easier. Whatever the position is there, like in matrix we are finding this is 1 1, 1 2, 1 3, 2 1, 2 2, 2 3, 3 1, 3 2, 3 3. In the same order you have to write here. So no need to remember, just okay. At first position means cos I1, I1. And the same in this case cos, this will be 1 2. So 1 2. Then 3 1. That's all. Like this one. And minus same I1 M1, M1, because already we had seen in all the plane I2, N2, M2, I3, M3, M3. In which plane it's rotated. For that only this new M is added. So now, sorry for this one. So just see here. Same again in this what? In this the direction we are adding. So now sigma 1, M1, tau 1, 2, M2. So this already we had seen. Now just in that plane we have to change. So here just see, again we will multiply, then what happened? This will be n1 square. Then n1, n2. This term will be here. Right. So again multiplying this, expanding and collecting all the terms. So sigma 1, n1. So sigma 1, n1 square from here. Now if you will take, then here sigma 2, n2 and n2. So sigma 2, n2 square. Then next here sigma 3 n3, so sigma 3 n3 square. Then so after multiplying, already I showed you how to multiply, so you will get this one in that plane. Now in the rotated plane, this once we have this one, so same, this star becomes what? N1 square becomes I1 square. Already we had seen this one. Sigma 2 I2 square, sigma 3 I3 square. Now whatever the plane is there, like here N2 N3, so this will be I2 I3. So here I2 I3. Then N1 N3 with 2 tau 1 3. So 2 tau 1 3. Now this one becomes I1 I3. So 2 tau 1 2, 2 tau 1 2, N1 N2. So 2 tau I1 and I2. Now we projected in that plane. So now what is that? I1 I2 I3. That is the direction cosine of the unit vector I. So what here? This is the direction cosine. Somewhere you can see the direction cosine, generally we are represented by L also. So you can take that as L also. So don't get confused with no L and I. That is just the direction cosine of the unit vector. Similarly, you can find for what? Sigma 2 star, sigma 3 star. So sigma 2, the direction cosine will be M1, M2, M3. For sigma 3 star, direction cosine will be N1, N2, N3. Okay. And for first L1, L2, L3 will be the direction cosine. Now just combine all these three. So just see here. After that what happened? Tau 1 2 in one direction. So sigma 1 L1 M1. Sigma 2 then L2 M2. Sigma 3 L3 M3. Now earlier that becomes a square. But in next case when we change the plane, that term again here. Just this step. So just you have to repeat this step instead of S. Now that will be the M. Okay. So with this we'll get this one. Now convert this into the matrix form. So what we will get? Sigma 1 star. Okay. So all the diagonal similarly sigma 1 minus sigma 2. So all the sigma will be in the diagonal element. And then first, so tau star 1 2, tau star 1 3, tau star 2 1, tau star 2 3 3. So wherever the position is there, again no need to remember, just only the diagonal you have to keep the sigma, that is sigma 1, sigma 2, sigma 3 with the star because it's a rotated one, and remaining according to their position you can just put this one. Now transpose of this RT will be what? Just this one. Right. So sigma 1, so just whatever this is there, that is star, not rotated one. Okay. So just you can remove the star and put this R. So this will be the final one. Now once just expand this one, that is invariant, then what we will get? I1 as sigma 1 star, sigma 2 star, sigma 3 star, which will be equals to by this, okay, according to this one. Okay, what we have? Sigma 1 plus sigma 2 plus sigma 3. Similarly for I2, now just get multiplied, sigma 1 star, sigma 2 star, that is 1, 2. How just see, how you remember? 1, 2, 2, 3, 3, 1. So these are, sigma will be outward, so positive. Now these three will be inward direction, so minus tau star, 1, 2, minus tau star, 1, 3, minus tau star, 2, 3. So these acting towards the I2. Now just again simplify this one. Similarly I3, so now in third, so 3 component will be there, L, M, N. In that case, so sigma 1 star, sigma 2 star, sigma 3 star, minus 2, 3. So sigma 1 into tau 2, 3 square. Okay, sigma 2, tau 1, 3 square, sigma star. So don't forget to put a star because already we are taking that invariant in the rotated one. Sigma 3. Okay, so finally what we will get? Sigma 1, similarly just converted, sigma 1, sigma 2, sigma 3, minus sigma 1, tau 2, 3 square, minus sigma 2, tau 1, 3 square, minus sigma 3, tau 1, 2 square, plus 2, tau 1, 2, tau 1, 3, tau 2, 3. Okay, so this will be the final for I3, this will be for I2, and this is the I1. Okay, these are the references where you can refer. Okay, if you have any doubt, you can just comment on the video or you can just contact me for your doubts clearing. We will see the doubt session also in separate video where the numerical things will be required, that we will see in a separate video. After finishing all the theory portion, we will see in video itself how to solve the numerical problems. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.